Neutron and charged particle spectroscopy. This is an outgrowth of a lot of work I've done with Pam Boss and in conjunction with Frank Gordon and with Stan Spock. I'm a renegade. I come from the hot fusion community. I worked in laser fusion from 1975 for about 13 years. I then was a visiting scientist at Max Planck on the Aztecs tokamak, and I was a consultant to the Lawrence Livermore mirror fusion programs. I was on the DARPA review panels for sonofuge until I got kicked off because I said it didn't exist. So I've kind of made the rounds. I'm going to emphasize neutrons today, and those of you who've seen some of our publications will recognize the triple track in the background. From Fukushima and beyond, that's really what this is all about. In 2009, on the 20th anniversary of cold fusion, The Economist ran an article and had a cartoon that I presume was Frank and Pam and Stan Spock doing electrolysis at Speyworth. You can see with great excitement. A few years before that, many of you probably know Buzz Lightyear, and he commented to Woody, are you still using fossil fuels or have you discovered crystallic fusion? So the work that we've been doing has been sitting around in the public eye for a very long time. Fukushima has a special role too. I was involved with Fukushima. I did not cause it. And Zeisler and I published a paper again about 6 months after that, analyzing residue that we collected 25 miles north of Fukushima Daiichi. Overview, I'll talk about diagnostics and trade-offs. We're looking at energetic radiation. I will specifically look at real-time energetic neutron detection and specifically liquid scintillator spectroscopy and damaging a high-purity germanium gamma ray detector, which is probably one of the most expensive ways to detect neutrons. Discuss briefly some witness materials, and then I'll emphasize solid-state nuclear track detectors, some acknowledgments, and some thanks. Well, for energetic particle diagnostics, you've had an awful lot of choices. And these are just the ones that we've used. So we've got solid-state nuclear track detectors, and they can pick off charged particles and neutrons. High-purity germanium, which is the gold standard for detecting gamma rays. It will respond to X-rays depending on the window, gamma rays, and neutrons, unfortunately for the neutrons. Sodium iodide, various plastic and liquid scintillators that are very sensitive to neutrons. Bubble detectors made up in Canada. Helium-3, which if you moderate it down, you can pick off thermal neutrons. Silicon barrier detectors for alphas, betas, and which is basic electrons. Proton recoil neutrons, witness materials. Again, typically these are from neutron activation. And liquid scintillators, again, alphas, betas, and gammas. But what are the trade-offs? Well, with the cryogenically cooled ones, first of all, they've got to be cryogenically cooled. This is extremely expensive and arduous, and a great way to destroy these is to let them warm up and then cool them down again before you've let them warm all the way up, and I've destroyed 2 crystals that way. It does have high resolution for gammas, but unfortunately it's sensitive to neutrons, and the neutrons damage it. Sodium iodide, gamma rays, typically 40 keV to 3 MeV. Relatively poor resolution. For the gamma rays, it's less sensitive to neutrons, which is good. The plastic scintillators without moderators will respond to charged particles and neutrons. It's sensitive to gammas. They're fast. They've got poor energy resolution and a modest efficiency for collecting them. Liquid scintillators, again, same kind of thing. Helium-3 will moderate it with polyethylene to slow the neutrons down because it wants to respond to thermal neutrons. Silicon barrier detectors, well, they're very good for protons and alphas with very high efficiency, high energy resolution, but they do prefer to be in vacuum. Bubble detectors, they detect only neutrons. They're integrating, but they have no time resolution. They have limited spectroscopic resolution if you spend the money on them, and they're only reusable 10 times. Proton recoil neutron detector is something that was produced at Los Alamos. They're really nice and they respond to neutrons. They have a flat response from thermal out to past 20 MeV, but they have poor efficiency and there's no energy resolution. Liquid scintillators responds to all 3, but again, relatively poor energy resolution. modest species resolution, and this is definitely not real time. And then the witness materials, again, they're by activation, generally neutrons. You've got poor energy resolution and efficiency. You know, 1 in 100,000 neutrons at the right energy might interact with copper or zinc. And that requires a relatively high flux to detect either the gammas or to look at the decay products afterwards, both prompt and secondary. Solid-state nuclear track detectors, there are really two flavors of these, but they will respond to charged particles and neutrons. They're insensitive to gamma rays. They're integrating detectors, so there's no time resolution, but that can be a good thing if you're looking at something that occurs very, very sparsely in time. They're immune to electronic noise issues like electromagnetic pulse. And this is very important in laser fusion, which is where I first became acquainted with these. The problem that you had was when you got over 10 to the 9th neutrons in, say, a nanosecond, you essentially have a small lightning bolt occurring within the plasma. That knocks out the front ends of all your diagnostics. Plastic doesn't care. There are two types of these. There's low temperature, typically CR39, Lexan, our explosive friend from the film industry, cellulose nitrate. These have high efficiency for charged particles, but lousy efficiency for neutrons. You know, if you see a track from a neutron, your efficiency is 10 to the minus 4 to 10 to the minus 6. That means a lot of neutrons pass by to pick up one recoil. The operating temperature range is from below room temperature to no more than 50 degrees C. The plastic begins to degrade above that. And you can etch it in basically boiling lye. You stick it in 6.5 molar sodium hydroxide, 70 degrees C for 6 hours, and you'll etch out the tracks. The high temperature ones, which is what I'm working on now, and this was in fact, this was because of Francesco Celani. They mount their nickel cell, their nickel wires, the copper-tin wire, around a mica strip. And at first I thought, look, this is an in situ witness material for charged particles and neutrons. But if you look at this, you'll see that you can't see through it. And for doing optical and potentially even SEM, it would be much better to have something that was clear. Well, I've used a variety of things, including glass slides and different kinds of glass. But in here, I have a piece of muscovite. It's about 3 inches long, it's 1 inch wide, and the idea is to superimpose that on top of one of these and wrap around it so you now have an in situ detector. The problem is, to etch the tracks in this, you've got to either use concentrated hydrofluoric acid or a plasma etching process, neither of which is terribly safe, both of which are very dangerous. So I'm not real fond of this, but it has an operating range from below room temperature to over 500 degrees C. So this gives you the opportunity to have an in situ charged particle and neutron detector within a high pressure gas chamber at high temperature. So what are the Leonard cold fusion issues trying to detect any kind of ionizing radiation, charged particles, gamma rays, neutrons? Well, in the electrolytic systems, the container itself and the electrolyte is not compatible with most detectors. You have to put the detector outside the device, but then you've got the problem, you've got R-squared losses because you're getting further away. You've got a solid angle problem. In addition, your X-rays and charged particles are all absorbed in the electrolyte or in the container. In the gas systems, again, the container and the high temperature are the issue. Again, the R-squared solid angle losses. You have the X-rays and charged particles absorbed, and again, the high temperatures and now the gas pressure precludes putting many types of diagnostics in. And then the other problem is you have EMP and EMI, electromagnetic pulse, electromagnetic interference, especially in glow discharge type systems. But what is nice is neutrons and hard gammas will get through. The problem is no one wants them. And this talk is going to emphasize fast neutron detection. So real-time energy resolved neutron detection. So for a real-time neutron detector, I take a liquid scintillator with a very large 5-inch PMT, and it will resolve neutrons both spectrally and temporally. The response of this is less than 5 nanoseconds. I can use a pair, it's got very good efficiency, about 5%. So 1 in 20 neutrons I'll pick off. A pair of these detectors can be used for time of flight. So I can basically set one detector to start my clock for gating and another detector here, and I only look at this detector when this one goes off. Now this is presuming, as several researchers have seen, that you get multiple neutrons off as a burst. So one of the detectors up close catches the burst, starts the clock, and this way I can cut my background almost to zero. In addition, I can use two MCAs, multi-channel analyzers, one looking at the time of flight, that's when signals arrive, and the other one to actually look at the recoil spectra that the PMT is picking off. Each neutron, as it rattles around inside that liquid scintillator, is going to give off a light pulse. And so this is called gated coincidence detection. This is classic physics. I've got two proton recoil liquid scintillators. One here, which is to provide my timing, it's close to the cell. One 3 to 10 meters away, which is my spectrographic scintillator. I go through a system that provides me with better than 2 nanosecond timing resolution. I then have a gating system, and one of the raw signals comes straight into this one, and the other signal comes over and recoils the spectra coming off. And this works. Taking two of these, putting one on top of the other, and using cosmic ray muons and neutrons, the muon comes in from space, hits the wall of the cave that I'm in, produces a cascade of neutrons. They're detected in both of these. So if I let it free run, the upper one I see a whole bunch of pulses coming through, and I see some pulses in the lower one. So multiple gate pulses being produced, multiple neutron recoils. If I then put it into single mode, then I have a window that's determined here, and I pick off one single neutron. Now, there's no point in doing time of flight with them on top of each other. But what it does show is that it works. I can then integrate the area under here, and I know how many light pulses corresponded. I can then pick off the energy of the neutron. In practice, you wouldn't put them on top of each other. You'd put them at a distance from each other. And that way, a spallation event that might hit one, chances are it won't hit the other one. That's how I cut the background down. So I'm doing, in this case, cosmic ray astronomy with coincidence gating from the muon-induced spallation neutrons, and it does work. So we've got a slower time of flight MCA here. We've got a very fast one we borrowed from colleagues in Korea that's 400 megahertz. We have a high voltage supply that drives the two PMTs, and then we've got a NIM bin, this is nuclear instrumentation module bin, for doing fast timing to tie all this together, the timing and the gating. Well, you got to characterize these, and this is where the first problem with this technique comes up. This is my background, and this is energy going off this way. So I've got a fair number of counts because wherever I am, I'm going to get spallation events. Cosmic rays are coming in, they're hitting, they're producing neutrons. Some of the muons come in, probably right in the beginning here. It's also sensitive to radiation in the background. This is cesium-137 source, and so I get a characteristic peak for that. So I look at plutonium beryllium neutrons. This is a spontaneous fission source. It actually has 3 peaks. I've picked off probably 2 of them here. If I looked and expanded this region, I might see a 3rd peak in there. I look at a californium source, which has a peak at 2.5 MeV, and then it just runs out to as high as 7 or 8 MeV. So I can see these, but you notice the background is, maybe 10 times lower than these sources are. So the problem is I'm also sensitive to neutrons in the background. So I'll look at a high purity germanium neutron detector, and as I note here, this is not a good idea. The only reason it's not a good idea is it becomes kind of a one-shot device. Once you've damaged the germanium, unless you're very lucky, depending whether you're an N-type or a P-type, it's either damaged for good or Ortec will happily re-anneal it for you for $5,000. They're very happy to do that. So first of all, this is a cryogenically cooled germanium gamma ray detector. We've worked with both beryllium windows, so we can see as low as 5 keV up to 3 MeV, or with an aluminum window, we can see from 40 keV to 3 MeV. So you can imagine we put the detector as close to the cell as possible. We put it in a lead cave with about 2,000 pounds of lead because the building is more radioactive than what we're looking at. And because we're up close and personal, if there are any neutrons, especially fast ones coming off, then they'll interact with the germanium. Now, thermal neutrons cause the germanium isotopes to activate. And this gives you a very classic line below 1 MeV, around 600 to 700 keV. Fortunately, we don't have many of those. Unfortunately, fast neutrons actually cause electron trapping defects. They actually knock the germanium atoms in this single crystal of germanium slightly out, producing a hole, making it hard to get the charge out. We didn't really know that when this happened. Normally, we would take the data, once a day. Pam Boss was running this one and took 5 measurements. And at the low end here, this is keV in energy. This is an arbitrary scale here. We have nice sharp peaks from the lead lines from the lead cave. And as we are running, they're getting uglier and uglier. That's the scientific term for what this is. That's called ugliness. And we gave this detector back, we told our colleague who loaned this to us with the DOE lab what we saw, and he said, well, run the software and it will fix it. We went to run the software, but never got a chance because the computer died. So we told him this, and I said, look, I've called Ortec, I'll send the detector back and maybe they can fix it. He said, no, I'm gonna come and get it. So he drove out from Albuquerque and took our detector away. But we'd saved the spectra. I showed it to Ortec, and I asked them, is this an instrument failure? Is this a computer software problem? Or is this neutron damage? They said, oh, that's neutron damage. Send it back, $5,000, we'll fix it for you. Everything is $5,000, it's a canonical amount. But we still wondered what went wrong. So we took a place in the spectra, and Pam did this, out around the K40 line. There's nothing else out there. It's 1.46 MeV. And beforehand, you have a nice Gaussian symmetric peak. After running it, this peak looked terrible. It had roughly the same area under the curve, but it would now be fit by 2 different Gaussians. It had kind of slept over here to the low end. And Pam did another little search. We found that somebody had the same thing happen. Apparently, using a cobalt-60 source, they found out that after neutron irradiation, it had kind of pulled over to the side. And this is now a recognized problem, especially for people working with neutron sources, say DD fusion generators, down a hole looking for oil, and then they stick down their germanium detector and forget to turn off the neutron generator. And they fry their detector as a consequence. But what this did is it showed us that the damage was consistent with an average neutron flux of 10 to the 6th neutrons per second for 24 hours. That's a commercially significant number of neutrons. Well, there was one more thing. Our colleague took a look at this, Pat McDaniels, and if you look at the way in which the baseline had been broadened, if you were to subject this to, say, a fission spectrum from uranium fission, you would have a peak around 2 MeV and it falls off, but the neutrons coming off would cause damage, and that damage would show up as a rise in the baseline, but it falls off like this. However, in our case, the baseline just kept going on all the way out here to almost 360 keV, which is indicative of the average neutron energy being over 6 MeV. So one of the advantages of damaging this detector is it told us something about the spectrum, the average spectrum of the neutrons. Okay, witness materials. Alan was talking about, wherever he went, was talking about transmutation. Again, this is work that was published by Stan and Pam, Chuck Young and Frank back in 2005. And in this particular case, a little spot, you kind of recognize this SEM and this mossiness. These 2 different points show, among other things, producing aluminum. Aluminum will not co-deposit an aqueous solution onto a cathode. Chemistry is wrong. That aluminum was produced in situ. This was not from a raw piece of aluminum. This is from aluminum chloride dissolved, and there was no aluminum in there. In addition, there are other pieces. There's iron and chromium and things. So each of these are indicative, at least in my mind, that what's happening in these spots where you get the reactions to occur, you now have these witness materials being produced as a byproduct of the fission of palladium and potentially fission of those products. Say palladium going to iron, iron going down to aluminum. Well, if you've got neutrons, take a piece of uranium wire, put it inside of a glass capillary, put it up close and personal, and what we see is the following. This is a liquid scintillator. It has 1,000 channels. This is basically the log of the channel, but this is energy here. Out here is getting out towards, at least for betas, is out around 2 MeV. This is what the cathode, which is a gold palladium wire, it has nothing. Red is what a snippet of that piece of uranium wire looked like before we ran it. And the blue is what it looked like after it sat inside the cell for a day. We have rearranged what's going on in there. And in fact, this evolves with time, indicative of different species being produced. And in doing experiments like this, we have generated as many as 160 gamma peaks. And we have to run this again because I've got the counts, I've got the identification, I don't have all the curves. I do have some of them. That was a question that goes back to Vancouver in 1997 from Peter. Where's the beef? Okay, solid-state nuclear track detectors. This is the molecular formula of CR39. It's a polyallyl diglycol carbonate. It's taken me almost 3 years to be able to pronounce that. And what happens is neutrons scatter off these, and the recoil atoms will then leave an ionization trail. And then when you etch this in sodium hydroxide, these trails go from being about 2 nanometers, they'll go up to anywhere from 2 to as much as 30 or 40 microns wide. It's very unusual to see CR39 edge on. Usually look at it from the side. In fact, it's amazing that they took the CR39, which if you imagine is my hand, and they took a knife and they cut it, and they look on the edge and see if there are any tracks. If there weren't, then they cut it again, looking for tracks. No one looks for tracks on the edge. They look at them straight on. And a colleague of ours, Gary Phillips at Georgetown University, and Gary was at the Naval Research Lab for at least 25, 30 years working for Dave. Gary was also the person who probably did the most to make germanium field rugged, and a lot of work in Dave's department and Gary's went into doing that at NRL. If you take a plutonium oxide source, which is a natural fission source, and put it in the vicinity of CR39, you end up with an enormous number of tracks. And these are recoils. Recoils of hitting the hydrogen, hitting the oxygen, hitting the carbon, knocking them, and then etching it. But you'll notice there's a whole bunch of smaller tracks. What that means is because the efficiency is so low, about 10 to the minus 4, chances of a neutron hitting something on the surface aren't very good. They're a little bit better as you go in. So if you repeatedly etch through there, these little tracks will get bigger. Now when we started doing this, Pam and I both labored under the misconception that the big tracks would go away, and we'd be left with little tracks getting big, and we'd be able to count them. The truth is the big tracks get bigger and uglier, and tend to overshadow the little tracks, but the little tracks do get bigger. And this has become extraordinarily important in a variety of places. One is with the International Space Station doing both human and instrument dosimetry, where you've got CR39 being flown, and there are stacks of CR39 titanium, CR39 titanium. The titanium is there to block charged particles. And you can see here there's a whole variety of identified. There are various fragments, high Z materials, silicon group, there are protons. If you hit carbon, and I'll talk about this more, hard enough, with a neutron, you can actually shatter the carbon into 3 alphas. In laser fusion, same thing. You've got 3.3 MeV protons, you've got 3.3 MeV alphas, you've got tritons, and there's a whole bunch of neutrons coming out as well. You don't want to do this manually. We do. At various times we've had available to us a Tassel scanner from the folks in Bristol, and this is a remarkable device. It's got a green laser. It will scan a 1 centimeter by 2 centimeter chip in about 2 minutes, producing on the order of 400,000 images. And as Frank mentioned, we got a patent that issued system and method for generating particles. This was last April. And I'm going to show this because this is important as to what I'm going to show you next. We'll take a piece of CR39 and make it as close and personal as we can. In this case, we've got 3 cathodes, platinum, silver, and a gold. We've also, in this case, got 2 electric fields. These are at 6,000 volts. But these have also got ripple, about 6% ripple, so that means they're inducing a magnetic field in this direction as well. And then you can see how it's set up. You've got a regulated supply, somewhat regulated supply for these, and we've got a Princeton Applied Research potentiostat, which is driving the whole system, and the anodes above it. So it's a platinum anode, and down here we get a series of wires we'll then co-deposit palladium onto. So if we run the experiment, and then we pull the CR39 out, and we look at the front and the back, first thing we notice is, I've had to scale this down because there's actually over 4,000 or 5,000 tracks in this small column. And generally, this is the major axis, this is the number of counts. So if it's circular, the major and minor axis are the same. If it's elliptical, the major axis is the long axis. So on the front, we've got 3 regions. This one, though, is about 5,000 counts in this particular experiment. On the back side, we still have some, but there's only about 140 counts now. We also have an alpha standard there, and those tracks fall right in this region. But then we've got this whole strange structure, and it actually goes all the way out to about 50 microns. And what this is indicative of is this is most likely alphas. These are very fast protons. These are neutrons, because an alpha will not make it all the way through the detector. We've already got some limited spectroscopy here. It'll take 40 MeV for an alpha to go from the front to the back. It'll take 10 MeV for a proton to go from the front to the back. So if we've got protons here that are over 10 MeV, a few of them went straight through, and they leave this little signature out here at the end. Another value of using CR39 is it gives us spatial information. So on the front, we can see tracks from 3 of these wires. On the back, we can see from 2 of the wires. Strangely, the silver wire is missing. It has no tracks in the back. Now this has 2 effects. One is, okay, if this is just chemical damage, how does the chemistry know that there's silver on the front and it shouldn't put tracks on the back? And then the additional question is, why are there no tracks in the back from the silver? And Pam and I are debating, there are 2 things here. One, this is likely the minimum in the electric field. Also, if you look at the Z of platinum, silver, and gold, well, silver is the least of all of them. Maybe it has the fewest neutrons, because most likely these are neutrons on the back side. There we go. The way this works, a neutron comes in, hits something somewhere within the plastic, and produces a recoil ion. That ion, if it doesn't make it to this edge where we're etching, and we only etch away 6 to 7 microns of plastic, we won't know there's a track. If it's close to the edge where it stops, as we're etching, we might get a little dimple. That's where the little tracks come from. Another case, we hit an ion. We actually have a nuclear reaction that will cause a spallation event. We'll knock a proton out. We might pick that off. And then the third case, where we've got a very heavy ion, carbon or oxygen, and we hit it, we'll produce 3 or even 4 alphas. We'll produce another neutron that comes off, but given that the original neutron had about a 10 to the minus 4, you got another 10 to the minus 4, so we're not going to see that secondary neutron. And Gary Phillips has done an awful lot of work, as I showed earlier, with DITRA and DOE sponsorship, that showed you could do neutron spectroscopy with this system. And if you overlay 2 of his curves, calibrations at 2.45 MeV in red, 14.8 MeV neutrons in blue, and you overlay the palladium co-deposition, you find that we lay right inside here, indicating we've got a combination of 2.5 and nearly 15 MeV neutrons. In conjunction with a colleague of ours, Pierre Carbonel at a Catholic University in Belgium, we took, well, I'm getting ahead of myself. First of all, we did an experiment with the Department of Energy. We used their DT generator and we produced some tracks. Pam Boss developed a technique to take a picture at the surface of the plastic and a picture at the bottom where the track ends. Superimpose both of them, and you can see where the track was, where it originated, and you see where the outer part is. And if you look at a DT fusion track and you look at a palladium deuteride track, I beg if you can tell the difference. We then took this with a scanning electron microscope with very, very low current, and we actually were able to indicate to Pierre, in the case of one of these, exactly what's in there, and we find that you can detect all of the structure inside here. You can see the whole thing. Now, when we're doing it optically, we're coming from the bottom through. With an SEM, we're going from the top down. Three more triple tracks. Again, here's another example from the Department of Energy. There are two alphas coming off, one going straight in. You run a chance, in fact, a high probability, that when the neutron comes in, it'll come in at any angle. It may hit a carbon. The alpha might come straight out. It may go straight in which case we don't etch it. It may go off to the side. Pam has made a habit of looking for what we call symmetrical tracks, the pretty ones, because you get three coming out. But you see the same thing. This is titanium deuteride using an E-beam experiment, palladium CODEP, and with a Department of Energy DT generator. But because the efficiency is on the order of 10 to the minus 4, for every one of these that you see, you had 10,000 or more very fast neutrons passing through that detector. Rogues Gallery, again, these come in all sorts of sizes, but this gives us a very good way to understand what is happening in these experiments. And generally, we don't see more than 5 or 6 of these in a given experiment. This is some work that we have done. The Russians did a beautiful job of getting around an ambiguity in the energy spectrum when we do this. Between roughly 1 and 8, or actually about 2 and 8 MeV for the neutrons, the types of tracks that you'll get out are almost the same. So you can say, well, I have a neutron between 2 and 8 MeV, but I don't know what it is. And what Andrei Lipson and Alexei Rosetsky did is they took CR39, put it in front of a cyclotron beam, changed the beam energy of the protons from about 1 to 4 MeV, compared the circles that you get, circles where you've got a track, a proton came straight in, normal to the surface, it went straight through, it hit something, it left a track. Then compare that to what you find from just straight neutrons. In this case, a californium source, which is in the black, and the CODEP work actually done at SRI. And what you find is there's a peak at about 2.5 MeV in this 0.5 to 4.5 MeV. And it's very monochromatic between 4.5 down here. You've got some scattering going on, but this is coming out of a cold fusion experiment, if you will. A 2.5 MeV neutron, which is consistent with DD fusion, one of the channels. We have a colleague who then analyzed NASA over 35,000 tracks and found a whole variety of these. And we're talking about, in this case, 10 to the 4 tracks. This 12 MeV track out in this region here is indicative of a helium-3 deuterium reaction. We've had some discussion as to what's going on here. He's classified these as alphas. These are a combination of alphas and neutron tracks through here. And we've published 2 papers on this in particular. In 2009, triple tracks in CR39. That was, as it turns out, that was 70 years after fission was discovered. The paper by Hahn and Strassman appeared in the same issue of Nature Wissenschaft in January of 1939. Our paper came out in January of 2009. In 2010, this is with the Department of Energy Lab and with the DOE National Nuclear Security Agency claims they provided some of the funding for some cold fusion. You can find this on the DOE site. So if DOE says they've done nothing with cold fusion, this paper says something otherwise. Now, there's been a real question when you see these kinds of things. This is a cluster of tracks. And going through the literature, I discovered the black beast of Arv. And you'll notice the relationship down here between all the eyes of the black beast, those of you familiar with Monty Python. So it's not clear what kind of creature this was, or it might have just been a radioactive dust bunny. So in summary, the nuclear effects caused by these energetic neutrons and charged particles can be observed a variety of ways. There's more real-time work required. Cosmic ray spallation neutron flux is inconsequential. That has nothing to do with what's going on here. I've got a paper, in fact, the spallation neutrons from cosmic rays are between 6 and 8 orders of magnitude below what we observed with our system. which on the average is producing about 1 to 2 neutrons per second from the entire experiment. There's a statistically significant number of tracks observed with CODEP, and we're talking about over 10 to the 5th tracks per detector. This is not 5 tracks or 10 tracks. Our background is on the order of a few tracks per square millimeter, and Pam, Gary Phillips, and I hand counted the tracks in one of those tassel images. The image is roughly 560 by about 600 microns. What we counted was 2,500 tracks, plus or minus about 10%, which works out to over 10,000 tracks per square millimeter, as opposed to a background of 3 or 4 tracks per square millimeter. It's statistically significant. There are multiple nuclear reactions that we've seen with exit channels. Fast neutrons, 2.5, 6, 14 MeV. Fast protons, 3 MeV, 7, 10, 14. Fast alphas, potentially up to 16 MeV. The results have been published in peer-reviewed journals, and as I said, a technology has been patented. And this has been a cooperative, multi-country effort to make this possible. I mean, this is the list of papers as of the middle of, or the end of last year. There are now over 37 papers relating to our work and some colleagues' work in the CODEP field. These are some of the issues of covers, or not covers, some of the issues that showed up in Naturwissenschaften, ACS with triple tracks on it, the European Physics Journal of Applied Physics, this is radiation measurements. So they're not all within the Leonard community's house organ Bavarian's journal, which we've got a number of papers in, but it has appeared in a whole variety of places out here. And as the Economist noted, the beast that would not die. And you know, this is just some of the acknowledgments. Fran Tanzella and Ben Earl at SRI for conducting what we call a palladium deuterium experiment with the Ben protocol. When you get CR39, it has a 60 micron barrier over it. You're supposed to pull it off, and Fran discovered after Ben assembled it one summer as a student that he'd left it on. And the question is, do I stop the experiment, pull it out, try to reassemble it, or just say the hell with it? By virtue of the fact that he said the hell with it, it meant that no chemical damage was occurring. And so now when the Russians looked at this, they kind of had to take it seriously. Another colleague up at Berkeley who tried this, took it off, they said, oh, it's just hamburger. And in fact, Andre Lipson, back in 2007, he and I had an argument. Was it just chopped hamburger that we saw on the CR39, as he insisted, or was it, as I insisted, caviar? And the Ben protocol allowed us to show that at least the majority of it was caviar. Alexei Rosetsky, and unfortunately Andre passed away a couple of years ago, did the spectral analysis and had been using CR39 for a very long time. Dazheng Zhao, then at NASA JSC and universities doing Space Research Association for doing the data analysis. The DOE Special Technologies Laboratory up in Santa Barbara for their DT fusion generator. Pat McDaniels for his gamma ray assistance. Our very good friend of the community, Dr. Lee, who was the first person to use CR39 in Leonard. George Miley for suggesting that Pam and Frank ought to consider this at ICCF in Marseille, France. Frank for all the managerial support at the US and the S. I was told by the attorney of the NXXY and SXXR to be proper and never ever use the fact that I've ever had anything to do with the Navy or space work. I noticed I said it's nothing to do with. I just said I had nothing to do with it. And so I have honored his request. Gary Phillips retired from NRL for his detector analysis. Dr. Jay Kim, my business partner, for continued support. And of all people, Johan Frenji from the Department of Energy, University of Rochester, and MIT, he works with Parker over in the fusion facility, for acknowledging our DT triple tracks in the British magazine New Scientist. Now, this is very interesting because I had worked at the Laboratory for Laser Energetics, which is how I knew about CR39. And shortly after, Pam had shown me some photomicrographs that caused me to move from Virginia to San Diego. I showed these to Johan. Now, Johan knew I'd worked in laser fusion. He assumed that I had some huge black program with the Navy making tracks, huge lasers somewhere on somebody's aircraft carrier. I think he was probably somewhat surprised when he got called just after the 2009 ACS meeting to find out what did these triple tracks mean that Ham had produced and had been published by our public affairs officer. But he said, yeah, they look like the real thing. In fact, laser fusion refers to the DT fusion triple tracks as nuisance tracks. The reason is they know they've got tritium. So when they get these triple tracks, they're obscuring something they care more about. They look at the tracks the neutrons make to know what the core density is. So we've been able to make use of an awful lot of work that comes out of laser fusion in the work that we're doing. And of course, thanks to Mitchell and Gail and even Peter, who claims he didn't do anything, for this and all the previous colloquia, and especially this year on the 25th anniversary of Martins and Stan's prophetic, though and not by their doing, premature announcement that was forced on him by the president of University of Utah. And I don't know how I can show, I've got a video of Martin. I took this back in 2009, just after the 20th cold fusion anniversary. I don't know how we can hear this. You all come up real close. Well, let me start it up here.
We can't because we're going to take a break afterwards. Why don't you come up? It's a good idea.
Okay.
Come on.
Well, I'll tell you what. While you're getting ready, I'm going to put up something else here first.
There we go.
This is the future of consumer CMNS refueling. And this is approved by Buzz Lightyear, by Woody, also courtesy of Back to the Future. So there's your Mr. Fusion.